All right, in this section, chapter 6.2, we are going to talk about energy, energetics, and this thing called activation energy, which is really important for chemical reactions in biology because we're going to have to deal with that. So, energy, we need to define what energy is. We'll talk a little bit about something like kinetic energy versus potential energy, which is more representative of like the chemistry we're talking about. And then we will discuss the concept of free energy and activation energy and talk about these two terms, endergonic versus exergonic reactions. So let's look at energy. So energy is just the ability to do work. We probably think in kinetic terms, right? We have water trapped behind the dam. It flows downhill and it can do work in the process, spinning turbines or whatever like that. Chemistry is very much like that. You can have energy that is stored in molecules and it can do work as well. So our kinetic energy, that is the energy of motion. So when you have high kinetic energy, an object is in motion. So let's look at the going down the roller coaster example, right? When you're at the top of the hill on the roller coaster, you have high what's called potential energy. Gravity can pull you down, doing work in the process. So as you move down, you start to gain kinetic energy. So potential energy is possible energy that has the potential to do work, whereas kinetic energy is that energy in motion. Okay, we're not going to worry too much about kinetic energy. What we're going to worry more about is potential energy that is stored in chemical energy. All right, so here we have our chemistry, and remember we talked about in chemistry, bonds are energy. Well, a molecule of hydrocarbon here, like this race fuel that goes into the race car, has a lot of potential energy. That is chemical energy. That's potential energy stored in all the bonds here, right? Each of these bonds is stored energy. And if we break those bonds, we can release that energy. In the race car, it goes into the engine and it is ignited, and that burning releases the energy in those bonds. Cells do the same thing. You bring in molecules that have lots of bonds in them, like glucose, and break the bonds, releasing the energy. You do it in a little bit less vigorous manner than the race car engine, right? Although there is a lot of potential energy in the bonds in your body. So we'll talk about how we actually control those reactions, right? This is a very quick reaction that happens in the race car engine. In us, it is much more controlled. Okay, so that's chemical energy, the potential energy stored in chemical bonds. That's going to be really important for us. So let's review, right? That burning of the race car fuel, that's a catabolic reaction, right? Taking a large molecule, breaking it down into smaller ones, and releasing energy in the process. That is going to be coupled, that energy is going to be coupled to anabolic reactions, where we take small molecules and assemble them into larger ones, consuming energy in the process. So these things are going to move kind of cyclically. All right, we are not going to get too deep into this, but it is important to be able to quantify things or put a number value on things in science. So how do we actually quantify chemical reactions and the associated energy that's involved with them? We are going to touch on this at a very surface level. Again, if you take chemistry or have already taken chemistry, you probably have seen these things or will see these things in the future. So one key concept here is this concept of free energy. This is not like unlimited energy, free energy device, right? The fake videos you see on TikTok and Instagram, right? Where the fan keeps spinning because you put two magnets next to each other or whatever forever. No, this is energy that can do work. The measure of energy that's transferred, really, right? So it's putting a number on how much energy is moving. And it's called Gibbs free energy for the guy who named it. But what we need to know is about how do we kind of calculate this? We're not going to do any calculations, but we just want to know a little bit about what's going into this. So Gibbs free energy is tied to one of the laws of thermodynamics, the second law of thermodynamics, which is all energy transfer involves losing some to heat. That's called entropy. Okay, so Basically, no chemical reaction is 100% efficient. You're always losing some to heat. So it starts with the sun, goes to the plants, goes to the animals, right? At each stage, we're losing some energy in the transfer as heat. So Gibbs free energy looks after entropy is accounted for. So it's calculating the amount of usable energy in a reaction. And it is shown as delta. This is the Greek letter delta. It's the uppercase delta. Delta G. Delta stands for change. Okay, whenever you see a delta symbol, that means change, which means basically subtraction. So change in free energy is delta G. Every chemical reaction results in a change in free energy. That could be positive or that could be negative. We'll see that in just a moment. But let's briefly talk about how this is broken down. Delta G, the change in free energy, equals the change in enthalpy, the total energy change. Don't worry about what that is, really. It's just the total energy that's changing in there, minus heat in degrees Kelvin times delta S, which is the change in entropy. So that's after entropy is accounted for, okay? This is the technical definition. I do not need you to know this. I just want you to have seen that there are these factors in here. So if you go into chemistry class, this is not blowing your mind there, right? There is always heat involved, and there is some loss to this thing called entropy there. But there will be a total change in energy after that. Okay, how do you measure this? Well, we measure this in energy per mole of reaction product. Remember, a mole was like a set number of this. So this could be something like kilojoules per mole or kilocalories. Now, kilocalories is actually the calorie on like the food packaging. That is a kilocalorie. So if it says 1 calorie on your food packaging, it's actually 1 kilocalorie, which is 1,000 calories. 1 kilojoule is equal to 0.239 kilocalories. That just there to say that these are different scales a little bit, but they're measuring the same thing, energy, okay, per mole. Just to further kind of ground these units of energy here, 1 kilocalorie is the energy needed to raise 1 kilogram of water up 1 degree Celsius. Okay, that's how we define this. So if you have a kilogram of water, it's 2.2 pounds of water. The energy required to raise that 1 degree Celsius is a kilocalorie. That's energy, right? I hope that like starts to put this unit into perspective here, right? Like you're putting energy in to heat it up. Okay, what we really need to know about is the sign of delta G. Is delta G negative or is it a positive value? That's really what matters at the end of the day for us, because if delta G is negative, it means the chemical reaction has released energy. We call these exergonic reactions. They release energy, and they are spontaneous. Now, that term spontaneous means something different than what you might think it does in everyday language. I'll come back to that in a second. If delta G is positive, that means energy is being consumed by the reaction. It is an endergonic reaction, a non-spontaneous reaction. Okay, hopefully you're seeing the connection here. We've talked about catabolic reactions where energy is released and anabolic reactions where energy is going in. These things are related. Okay, let's talk about this spontaneous bit in chemistry. Okay, a spontaneous reaction is not one that happens instantly, like what you think spontaneous means, right? A spontaneous reaction is a reaction that will just happen, okay? It could happen very, very slowly. The rusting of an iron nail outside takes a long time, right? You put a piece of iron outside, it does not instantly rust. But rusting is a spontaneous reaction. It's an exergonic reaction. It just doesn't happen super fast, but it is chemically favorable. Okay, it releases energy in the process. A non-spontaneous reaction will not occur without energy input, basically, is the long and short of it. Okay, so why do we care about this? We need to look at a graph of free energy. And here we have two graphs. We'll look at the exergonic processes first. So here's our free energy. The higher it is, the more free energy we have. we're going to look at the change in free energy between the reactants, the thing that goes into the reaction, and the products, the thing that comes out. And the sign of this is what determines what we're looking at. So you can see in this reaction, our reactants, the things that we put into the mixture, they have a lot of potential energy. Think of that like the race car. You pour fuel in and you add oxygen. Those are the reactants that are going in. They have a lot of potential energy up here. Now, something weird's going to happen here. You'll see this little hump here that we have to get over. We will come back to that. That is very important here. Just 1 second. But as the reaction proceeds, we will get a lower energy state in the products. So that means energy was released in this reaction. That means delta G is less than 0, which is negative, right? Exergonic reaction. Let's look at the opposite side of things. Our reactants have very low potential energy. To get them up to a higher potential energy in the products, we need to add energy to this reaction. That's where the non-spontaneous part happens. This will want to happen, right? This does not want to happen unless you put energy in. So that's our difference. These graphs are very important here at showing the different energy states. Again, though, spontaneous does not mean that this is speedy. Okay? It just means it wants to happen. It doesn't mean it's going to happen fast. All right, so tie it back in, right? Anabolic reactions, where we're taking small molecules and putting them together, consuming energy, is an endergonic process. Endergonic right here. We take the low energy state and put them together, build a higher energy state. That's anabolic reactions, or endergonic. Catabolic, on the other hand, we take molecules that are large, break the bonds in them, releasing energy in the process. That's an exergonic reaction, okay? So we've learned a little bit about the biological terminology, anabolic and catabolic, but we also know the chemistry terminology, endergonic, exergonic. These things are intricately linked here, right? Back to our chemistry side of things. So most chemical reactions, as we talked about, generally want to run in one direction, but a lot of them are also reversible depending on how much stuff you put in or things like that. Chemical reactions are going to run back and forth until they reach equilibrium in a closed system. Okay, a closed system is I put two things in a jar and leave them. No energy goes in, no energy comes out, things like that. To move away from this equilibrium requires energy, and we need energy to be input. That could be changing the amount of reactant or the amount of products. We could add more stuff to the front, more stuff to the back. The thing about biology is we are not a closed system. Cells are constantly bringing in new material, exporting waste. That's an open system. Biology will never reach chemical equilibrium. Technically, it does when you die, right? Like you stop all chemical reactions, you're at equilibrium. Okay, but cells are an open system versus a lot of chemistry talk in chem class is about closed systems. Same thing in physics, right? We as biological organisms are open systems. New stuff comes in, stuff goes out all the time. Okay, so back to our water wheel, right? Thinking about this, right? We have our input, our reactants, and they're at a higher energy state. They'll want to flow down to a lower energy state, releasing energy in the process. That's a type of chemical reaction, right? But we said that this will happen quicker if we pour more in at the top or take it out of the bottom, right? But also, if we start pouring water in the bottom or block it up, it's going to start to slow down, right? We get a higher level of products. We're going to slow the reaction down. You might even get to a point where it starts to run backwards. Chemical reactions, metabolism is like this, okay? So there's always this level of how quick is the reaction going and what direction is the reaction going. In this case, it generally wants to go in the forward direction, right? This way. But there are conditions that can cause it to go backwards. All right, now, there is this concept in chemistry that where our analogy kind of breaks down. I'm going to do an analogy here. Like you're pushing a car, right? You have a car that's in neutral and you start to push it. Initially, it's really hard to get that car going, but once you get it moving, you've overcome the friction, right? It's easier to keep it moving. Okay, that's kind of like this phenomenon that we saw in our graphs. This phenomenon is called the activation energy. It's expressed E subscript A here. Activation energy is basically a small input of energy that's required before we can release the energy. So in an exergonic reaction, we got to put in a little bit of energy before we can actually drop down to this lower energy state, releasing energy. Now, this energy is made up when we release it. So the only real change that's happened here is delta G, right? We started at this level, we went up here, but then we released. Then we look at whatever happens after that activation energy is overcome. In chemical reactions, it's often heat energy that is doing this by speeding up the molecular motion. Okay, heat in chemistry is about molecules moving around. So heat energy allows the molecules to overcome this. The activation energy determines how fast a reaction can proceed. So we could put a lot of energy in on the front end and overcome the activation energy. That'll speed up the reaction. Or there's another possibility. We could lower the activation energy and then the reaction would speed up. Okay. In the activation energy here, we say the molecule goes through what's called a transition state, kind of changes shape a little bit as it's going through this. Just mention that because that's a term that will come up in chemistry. You might hear in the future. Not important to understand the physical reality of what a transition state is, but the key here is that this activation energy is kind of limiting how fast reactions can occur. So when we get up here, right, it gets into a really high energy transition state that's unstable, and then it drops all the way down to release that energy. Okay, let's look at an example and let's see how we get over the activation here. All right. So in this chemical reaction, we have methane, CH4, that's our natural gas. We have oxygen, it's in the air. That will combine to form CO2, water, and in the process will release energy. So if you go home and you turn your gas stove on and you don't let the little igniter spark, the gas is coming out and it's mixing with oxygen. Technically, this reaction is occurring. It is occurring very slowly, so you will suffocate before it produces any heat, right? But it is technically occurring. What your stove does, though, is your stove has a little igniter on it that makes a spark. It goes click, 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 right? That spark is energy that's being added to the system to get over the activation energy. So then we can have this chain reaction that occurs called burning, okay? So the reactants, the natural gas and the oxygen, they need to get over this activation energy. The sparker on your stove provides that activation energy. And then we end up with the release of energy in the exergonic reaction that is burning. Okay, so the spark gets us over the energy hump. Okay, so that's how we deal with it with our stove. What about in biology? In biology, well, and other chemical reactions, but for biology, we need catalysts. We need catalysts to reduce the activation energy. So here's our original uncatalyzed reaction. A catalyst comes in and reduces the activation energy hump. That's going to speed up a reaction. And remember, in biology, enzymes are biological catalysts. They help speed up and control the rate of reactions in a cell. Okay, controlling the rate of reactions. That's an interesting topic to talk about because why? Why do we need to control them? Well, you might not think about it, but you are kind of like a marshmallow, okay? I'm not saying you look like a marshmallow. I am saying you are full of high energy nutrients, okay? I know the term nutrients and marshmallow doesn't seem compatible, but there's a ton of sugar in here, right? There's lots of energy. So what happens when you leave your marshmallow in the fire too long? It burns, right? So technically, you eat a marshmallow, there's enough energy in there for it to burn, right? To combust. Why don't you explode when you eat a marshmallow? Well, that's where enzymes come in. Enzymes control the rate of this reaction in our body's metabolism. That breaking down of the sugar in the marshmallow, like if you eat it, it doesn't come all in one hit. We break it down in a slow, controlled process that releases the energy and stores it and captures it. Otherwise, if we just released all that energy at once, we would explode, right? We would literally blow up, basically. There's enough energy in there for us to light on fire. So, we're going to look at enzymes as a means of controlling the rate of chemical reactions. That's their role in biology. Okay, that was a lot. You might need to go back and review that. A lot of terminology in there, right? But I'm using the chemistry terminology and the biology terminology just to mesh those two together. They're important. So we have a catabolic breakdown of glucose in your body. This is an example of A, an endergonic reaction, B, an exergonic reaction, or C, there's not enough information. Go ahead and pause the video. Think about that. Catabolic breakdown, that would be exergonic, releasing energy. So if we go back here to our release of energy, right, that's an exergonic reaction. Negative delta G there. All right, so we talked about energy here, right? That's the ability to do work. Kinetic energy is all about objects in motion. If you're interested in biomechanics or mechanics and physics and things like that, you'll talk all about kinetic energy. For us, we're really worried about potential energy, specifically a potential energy locked up in chemical bonds called chemical energy. So, chemical energy is stored in bonds, it's potential energy, and it's really of interest to us in biology. We're going to have anabolic reactions that use energy to build those bonds, and then catabolic reactions that release energy by breaking those bonds. We talked about how we can quantify a change in energy. That's Gibbs free energy, describes energy transfer. What we really need to know is, are we releasing energy? Is it a negative delta G, exergonic? Those are our spontaneous or energetically favorable reactions. Or is it positive delta G, endergonic reactions? We have to input energy into that, non-spontaneous. The activation energy is that hump that we need to get over before molecules can move through their transition state to release their energy. Catalysts reduce the activation energy, helping speed up reactions, and in biology, call our catalysts enzymes. All right, that's it for chapter 6.2.